Hey everyone, welcome back to mini lecture number 12. This is the last one. This is for Computer Science 252 at the University of Wisconsin-Eau Claire. Here we'll be talking about Pthreads, OpenMP and MPI, and then parallel computing in general. And required reading, there is none. Study for that exam, that final. Here are some self-check questions, which are more or less fair game for the exam, although again, I will be de-emphasizing this because there wasn't as much time or experience with it before the final. But things to think about are here. Here are some terms I'd like you to be familiar with. The first is a zombie process. A zombie process is a process that's finished its task, but hasn't yet been removed from the process table. So an example of this is if a parent spawns a child and then wanting to get the exit status of the child, and then the child runs, it does its thing, it completes and returns an exit status. And so the parent is waiting to get that exit status. The child is finished, so it's a dead child. That's morbid, but it hasn't yet given its exit status to the parent. So in that meantime, while it's finished but it hasn't returned its exit status, it's a zombie process and then when that exit status does go to the parent, then the child is free and it can be reaped, which is the morbid but technical term for it. Believe it or not. Then you have an orphan process, and an orphan process is kind of what you might expect. It's a child process whose parent process has been terminated. So the parent's finished, but the child lives on. Then there is concurrency. Concurrency, as we talked about briefly before, is when two or more threads or processes are live at a given moment. They've started and haven't finished. Now, a CPU may or may not be actually working on threads or processes at the same time. It could be that the CPU is taking turns. So if you have just a single core, a single processor, then it's each of the processes or threads are taking turns on that one processor. Or it could be a multiprocessor, and so maybe there are multiple streams of execution that are happening actually at the same time, but they're concurrent. Finally, blocking calls. And now this is more important for this lecture. A method is blocking, or sometimes called synchronous, when it doesn't return until it has completed its function or fails. Now this is really only applicable in multi-threaded or multi-process applications, because otherwise, if I call the square root function, you could say, well, that doesn't return until it's completed its function or failed. And yeah, you're right. So blocking calls are really only in the context of multi-threaded or multi-process applications. Examples include things like getLine or scanf. Now, technically, these are using a few other things under the hood. They're talking to the operating system. So yeah, they're dealing with other processes and other things. But for instance, getLine, if you're trying to get a line of text from the user, you wait for them to type their text and then they press enter and then getLine resumes. But until getLine resumes, or until the user presses enter, getLine just keeps waiting for the user to type input, and it could wait forever. Except when a server accepts a client request for a connection, there's two ways to call accept. One is blocking, one is non-blocking. The blocking one, which is the one we did in our lab, in that version, the server will sit on that accept solution or on that accept call until a client tries to connect with it. And so, if a client isn't connecting, the server just waits and waits and waits, and then there's a client request, and then it resumes. So that's a blocking call. A method is non-blocking or asynchronous when it returns immediately. So when that happens, the task that you call or that you ask for or request, that's going to run in the background in the meantime, and then later on, the operating system can notify the process that the task completed or failed. Or maybe that process can ask and say, hey, has this thing that I asked for finished yet? Is this IO complete? Or in the case of accept, if you have an asynchronous accept, the server will say, okay, I'd like to accept the connection. And then it will immediately return from accept, having made that request, but it will keep going as if it doesn't have that request yet. And then later on, it can check and say, hey, was that request granted? Do I have a connection now? You can look more into that in more detail on your own. We're going to look at Pthreads, OpenMP, and MPI. Pthreads is the first. Pthreads are really good if you want to make your own custom multi-threaded applications. Pthreads are from the word POSIX threads. And POSIX is a standard for Unix and Linux, as we've seen. So it's a standard library for working with threads. Historically, there was a lot of different chip manufacturers that had different ways of dealing with multi-threading. And so they all had their own API, their own way of dealing with threads. And so the POSIX standard sought to try to standardize them and make it so that you could create threads on different chip architectures using a single API, a single set of function calls. So to use them, we have to pound include pthread.h and compile with -l pthread. The idea behind POSIX threads is that if you want to create a thread, you create a thread and you give it a task to do. And then the thread will work in the background until they complete the task or are rejoined somehow. Let's see an example of this. In this example, you first pound include pthread.h, and the red text here is going to be the commands or the lines that are unique or special to the pthread library. Pound define num threads is 5, so we'll have 5 threads, and then we've got our main method. First, we're going to declare an array of threads. This will basically be the addresses of each of the threads, the thread ID numbers, if you will. We'll have a return code and t. T is going to be our counting index. So we're going to have a for loop here, and we're going to spawn 5 threads. So counting from t equals 0 to t is less than 5, so 0, 1, 2, 3, 4. T is going to be the index variable for each of those threads. So we'll print out, the main process will print out in main, creating thread, and then the rank or index of that thread. Then we call this command, or this function, pthread create. You pass it in the address of your array index, so it's basically going to fill in that thread index using an ID number for that thread. Pass in null, don't worry about that. We're going to pass in something called print hello, which I'll describe in just a sec. That is a function. So we are passing a function in as the argument for another function. Yes, this is totally valid, legit C code. Then we're passing in t, and t was type long. Now we're casting it as type void star. What the heck? What's going on? Let's get back to that in a moment. First, pthread create is going to return a return value. If it is not 0, then there's an error, and handle that error. But now let's go back to that pthread create. That's going to start a thread and have that thread call some function called print hello and pass it as an argument t. Let's have that function up now. So here print hello returns type void star. So that means that it's a pointer to a function. That's the notation for a function pointer oftentimes, not always, but that's one of them. And then it has argument list void star thread ID. Now the actual argument when you create a thread, when you create a pthread using that thing, you have to pass it a function, and that function has to accept one argument and one argument only. And that one argument has to be of type void star. Now that could be a pointer to a string. It could be a pointer to an integer. It could be an integer that you cast as a void star and then cast it back to an integer. That's what we do here with t as a long. Or it could be, a pointer to argv, and it could have a whole bunch of different arguments. It could be a pointer to a struct with, 500 different arguments to this function that you'd have to kind of unpack, if you will. So that's what that argument is there. So basically, you pass it this function print hello, and you pass it a pointer to an argument, a pointer to a void star, which then you could reinterpret however you want. That's up to you. In that print hello function, it interprets the thread ID as a long. So it makes it a long again, and then prints out, hello world, it's me, thread ID number, and then that value. And then it calls pthread exit. So then that thread is done, and that's it for that. But at the very, very end, the main process says, okay, now we're going to close down all the threads, we're going to make sure they're all done, and then we're going to be done with that. And then it could return whatever for main and exit the program. When we run this, what do we get? Here's the example output from that program. I can compile and run it on my own computer, and this is what I get. And you notice that right away that all of these different executions are different. And this is what concurrency is, because concurrent execution means that things are going to be overlapping and going out of order. In some cases, thread 0 gets created first. You notice that all of those are the same because that's all happening from the main process, and the main process is happening in order. So the main process is only going to create threads in order. However, when those threads get created, they could get run right away. They could take a while to start. They don't even have to start in order or not. That's concurrent execution for you. So lessons from that: concurrent execution means that threads or processes may overlap. They might be executing in parallel on multiple cores, or they might be taking turns on a single core. We don't know. That's up to the operating system to decide. One thread or process may complete before other processes even begin. There's no guarantee whatsoever on the order of the output to the screen. There's no guarantee to what order those operations will run. There's no guarantee on any of that. So that's something that we have to figure out on our own and try to work with. And I talk about some strategies later in this lecture about how to deal with that. Next up is OpenMP. OpenMP is really good for quickly parallelizing code with minimal changes to your code. OpenMP stands for Open Multiprocessing. It's a series of compiler directives, library routines, and environment variables that together help you be able to make multi-threaded applications a lot more easily than using Pthreads. Pthreads is great if you want to do things more custom to kind of say, here's what this thread does, here's what that thread does. OpenMP is better for creating a bunch of threads that will kind of do similar things. This requires installing the OpenMP library. It's not usually pre-installed, but it's pretty easy to do. And OpenMP is used to achieve parallelism on a single multi-core computer. So it's multi-threading more than multiprocessing, or true multiprocess. It's not using multiple processes. It's using one process with multiple threads. Now you can specify how variables are shared. Each of the different threads or processes will run pretty much the same code. They can branch a little bit, but they'll basically, it's kind of like when you create a clone of a process. It has a lot of the same variables. It copies over the variables. In the same way, when you spawn a new thread here using OpenMP, they're all going to share the same variables by default. But you can specify when you say, here's a section of parallel code, you can say the variables here, each thread is going to have its own copy of these variables by declaring those variables as private. Or you can say, you can give a list of variables and say that those variables are going to be shared. So you can specify shared variables and you can specify private variables. Shared variables, those are shared between all of the different threads. They can read to them, write to them, and everything. But private, they have their own copies. If you want to know more about how OpenMP works, there's a great tutorial here. It's very simple, very clear. I really recommend it. It's a great place to get started. Okay, so here we go. OpenMP.h, you got to include that. And then we've got our main method. We've got two variables, int n threads, so the number of threads, and then TID, thread ID. What we're first going to do is we're going to fork a team of threads, giving them their own copies of variables. So we have to use a preprocessor directive, remember that's part of OpenMP, called pound pragma OMP parallel. That's going to say that this next block of code between these two curly braces is going to, we're going to send messages to OMP, the OpenMP library. It's going to parallelize this block of code. So the threads are going to be created at the start of this block, and they're going to be done by the end of this block. Then it's also saying there's going to be, it says private n threads TID. We're saying now that the n threads variable and the TID variable, those are going to be private. So each thread is going to have their own copy of those variables. We could list, say space shared and then have a parenthesis surrounded list of shared variables. Not in this example though. Okay, so now at this part in the code, we're inside the block. So now we have a whole bunch of different threads that we're going to be running in parallel. And they're all going to be following the same directions. They're all going to be running the exact same code. As opposed to Pthreads, where you're saying, create a process, here's something for that process to do. Create another process, create a thread, here's something for that thread to do. Here's something else for that other thread to do. So Pthreads gives you more granular control, but it's harder to use because there's a lot more stuff you have to do. It's more low level. OpenMP is going to take away a lot of that thread creating and thread exiting and thread joining and stuff by making it a little bit higher level for you. So in this block, we have TID equals OMP get thread num. So what thread number are you? If you have 6 threads, are you thread 0? Are you thread 5? Are you somewhere in between? Then printf hello world from thread equals %d thread ID. So hello world from thread equals 5. And then we have a section that we're going to branch. Now, if the thread ID is 0, in other words, if you're the master thread, if you're the first thread here, then execute this block, and the others aren't going to do that part. So if you're the master thread, say n threads equals, figure out how many threads there are total, and then print the number of threads. And then at the end, all threads join the master thread and disband. So again, OpenMP, what it's doing here is it's taking care of all of that thread creation, thread exiting, thread destroying and stuff, making new functions and stuff. It looks like it's all one serial block of code. And if you were to run it without OpenMP and get rid of those OpenMP function calls, yeah, it would otherwise kind of sort of work. Like it looks like it's serial code. But because you're making OpenMP, it makes it parallel. So here's example output from that program. And so all of them start off saying hello world from thread 0 and number of threads equals 8. But other than that, all of the threads basically get scheduled out of order. So again, that's an example of concurrent thread execution. They're all, we don't know what order the operating system is going to be running those threads. Sometimes the last one is first, sometimes the first one is last. It all gets shuffled up and shuffled in order. And a question, if you're curious, is why does thread 0 always go first? And if you're curious, feel free to email me and I'll let you know. But don't worry about having to know that yourself. That was OpenMP. Now we move on to MPI, which is my personal favorite and the one I have more experience with. So with MPI, what's different about it is the first two are really good at doing multi-threading. MPI is true multiprocessing. So it's really good at making separate computers work together in parallel to do a common thing. MPI stands for the Message Passing Interface. It's an API, a standard set of calls, and there are different implementations of it. For instance, there are OpenMPI, which that's one of the main two standards. The other one is MPICH, MPI-CH. Both of those are well supported, used by lots of people. Just don't confuse OpenMPI with OpenMP. OpenMPI is MPI, OpenMP is what we had before. So MPI is a library of routines that allow you to talk to other computers. Now, most of the implementations of MPI behind the scenes are setting up communication between these other processes on these other computers, or sometimes on the same computer, using TCP sockets. So OpenMP somehow behind the scenes is setting up port numbers, it's setting up sockets and everything so that all the different processes can talk to each other. Now this is quite a bit more complex than just spawning other threads. But again, you're using other processes which can't talk to each other, they can't affect each other's memory except through sockets, so they need some way to do that. And because of this extra complexity, you actually have a new compiler. So instead of compiling with, say, GCC, now you would compile with MPI-CC. MPI-CC actually uses GCC under the hood, but it's a wrapper to GCC. So it does a bunch of other things in addition to just the usual stuff that GCC would do. You can still pass it a lot of the same arguments and flags and command line options that you would to GCC, and it will forward them to GCC, but it has a couple of its own as well. Then when you run your program, once it's compiled, you would run it using a custom executable program called MPI run. Now MPI run is going to not just spawn, it's not just going to run your program, but it'll actually ask you how many processes you want to run on. So in this case, I'm saying MPI run NP8, run 8 processes of my program. When I do that, it will launch my program not just on the computer that I'm currently on, but on all the other computers as well. Or if it's just on my computer, it'll spawn 8 processes on just my computer. And there's ways of setting that up and configuring and all that stuff. But it runs 8 processes, 8 separate processes, and gets them talking to each other. Each MPI process is actually a separate executing program. That's the biggest difference from before. OpenMP and Pthreads are all a single program, just multi-threaded. With MPI, whenever you compile a program, it's going to have a single program, which is nice, but it's going to, when you run it with MPI run, it's going to start that program not just one instance of that program, but in this case, 8 instances of that program. And you can specify what hosts to run on. You can say, do it all on this computer, separately. You can also say, like, if you've got the computer lab at UWEC, you could have that running, on that computer lab, and each one of those computers would be running a separate instance of my program. Now, if there are more requested processes than available hosts, then some processes will double up on the same host. So for instance, in a little bit, you'll see an example of how I used, I have a quad-core computer, and so I requested 8 processes, and so what it did is it doubled up. So each of my cores had 2 processes that would have to take turns. Here's what you do in MPI. First, you initialize the MPI environment in services. That gets all of the different computers talking to each other. So you could do that using MPI init. And yeah, this gets the processes talking to each other, it sets them up, sets up communication. Second, you can create a communicator or group. You don't have to. This defines the topology of the network. And if you have different groups doing different kinds of things, you could have different communicators for different ones. You can have a ring topology, a Cartesian grid topology, node topology. We'll talk about that later. It's cool. Every MPI process in a communicator has a rank. Now this is like a thread ID. It's basically saying, if you have a communicator with 5 processes, MPI processes, then they'll have ranks 0, 1, 2, 3, 4. And different communicators or different groups, an MPI process can have a different rank in different groups. So there'll be MPI com world, which is the total, all of the MPI processes being run for this parallel program. But then you could have subgroups, and each MPI process will have a different rank in each different group. And then each process will use its rank within the group to determine what to do. Am I supposed to be listening right now? Am I supposed to be sending data right now? Am I the server? Am I the client? And so on. So here's the an example topology. This is what's called a ring topology. So here I've got 8 different processes organized in a ring. And so in this topology, I might want to send data from process 0 to process 1. Now, yes, they can all talk to each other if I want them to. But if I have this ring topology, it's optimized so that process 0 can talk really quickly to process 1 and really quickly to process 7. And that may be good for certain kinds of algorithms or problems. Another topology is a Cartesian graph topology. So this could be either 1D, which is basically a ring, or a 2D, which is kind of like a torus wraparound boundary condition kind of topology. So here, process 4 is optimized to talk with processes 1 and 7 in the x direction, horizontally, and then processes 3 and 5 in the vertical dimension. And so it's really good at sending data to the left, to the right. And this is really good for certain kinds of problems in physics, where you've got, you separate, the ground into a 3D grid of boxes, and then you try to, or atmosphere into a 3D grid of boxes, and then you try to have each box talk to the boxes next to it. Because a block of ground right here has nothing to do with a block of ground 10 kilometers from here. But it does have a lot to do with the block of ground right next to it. So this is used a lot in scientific applications, and it's so cool. So in MPI, going on with the steps, you've initialized it, you've maybe created the communicator, or you've gotten the rank from the communicator for your group. Next is to communicate. So you can send and receive data just like you would with the client and server model. But MPI is awesome, and so it has a whole bunch of other commands too. And I'll show you diagrams of what this looks like in just a little bit. But there's a bunch. Finally, when you're done with all of the data sending and talking and stuff, you can finalize. You can close groups, you can close the entire program. So when you call MPI finalize, that'll terminate all MPI communication. It's basically shutting down the clients and servers, shutting down the sockets, and it's saying no more communication, we're done. Now this is a lot, it's all a whirlwind. Let's see what this looks like as an example. Okay, so here's an example of using MPI. First, we pound include mpi.h. You have to pre-install it yourself, but it's a standard .h file, and it installs to the standard location, so we use the angle brackets. Now, before we begin, it's important to remember that this is going to be a separate program, almost standalone program, that's going to be run on every process that we spawn when we run MPI run. So if I have 10 computers that are each running this in parallel, each of them are going to run the exact same program. They're just going to have slightly different numbers to start that. The only thing that's going to be different are the ranks. So each program will call MPI init, This is basically, you can pass an argc and argv here if you want, but we'll just pass null. No reason to use those other things. And this is going to start up the communication. Next, we get the number of processes. So each process is going to call MPI com size, and we're going to pass in a constant MPI com world. That's a predefined communicator, a group that's saying all of the processes in this program. So all the processes that are working together right now, all of them that have been spawned together, that's our group. And then what's the size of that group? Let's pass in an address of an integer, and it will set that value. Next, get the rank of this process. So now each process is going to call MPI com rank. So what's my rank in the communicator? In this case, the world communicator. So all the processes together. What's my process ID number in the world of this program? And so it will set that. And this is where it's going to be different for each process. Everything else is going to be exactly the same, but this one number right here is going to be different for each process. And this one other thing is going to be different too. I lied. The name of the processor, that will be different, right? So if I were running it on the thing servers, I would have thing 0, thing 1, thing 2, thing 3. Those would be different. So you can call, you can get the processor name. You can pass it in a character buffer, and it will fill that in. And then we can print off a hello world message. So hello world from processor, and then the name of the processor, which has rank, whatever the rank is out of however many processes there are in the world. Finally, when you're done outputting those, then you can call MPI finalize. Here's some example output from that command, or from that program. Here I've invoked the command MPI run-np8. So I'm requesting 8 processes. Now my computer only has 4 cores, and so when I ran that the first time, it actually gave me an error saying, hey, there's more processors that you're requesting than you have cores available. So I went around that by using the oversubscribe option. And so what that does is it says, that's okay, just ignore that. Just distribute them as best you can. So 4 cores, 8 processors. I'm getting 2 processes per core. Fair enough. But as before, what you're seeing is that all of these different processes are talking to me at different times. They're running concurrently, and there's no guarantee of which one's going to come in which order. That's, again, concurrent programming. You're used to that by now. Now, MPI can just send a little chunk of data from one process to another process, point to point, just like using this the client-server model. However, that's not always the most efficient way to do it. A really good way to do it oftentimes is to use group communications, and we'll look at some of those here. So one group communication is the broadcast operation, and when you broadcast data, you send it from one node or one process to all the different other processes in a communicator or group. That could be the world communicator, all the processes, or it could be a subset of that. So when you broadcast, you're sending one chunk of data represented by red here to all the different other ones. When you scatter, you chop up a data set or a workload into a bunch of different pieces, and then you send those different pieces each to a different process. So one process might have to do the red work, one might have to do the yellow work, one might have to do the cyan, one might have to do the green. And that way, you divide up the work, and hopefully you get a really nice speed up. Going down, gather is kind of the inverse of that. So say that you've scattered your data to the different processors in your group. Then you want to say, well, what are the results? Well, you can gather the results, and so all of those different processors will send you back a chunk of data, and then it will accumulate all of that data into a single buffer or array using the gather operation. Finally, there's reduction style operations, and so this could be addition, as is shown here, or it could be subtraction. It could be, there's a whole bunch of different kinds of operations that you can do. And so in this addition style reduction, it uses an optimal parallel algorithm to be able to quickly add all of these different numbers from all the different processes that there are, and finally get the result, in this case, 16. That's usually used for scalar stuff, but it doesn't have to be. There's also even fancier functions. When you use MPI_all and then gather, scatter, broadcast, reduce, etc., it will do a huge collective communication. So for instance, say I have 3 processes, 0, 1, and 2, And I start with red data being in the red process, green data in 1, blue data in 2, and I want all of them to have that. I can use MPI all gather, and what that will do is we'll send that same data, a little bit from each process, so that all the processes have a little bit of that same little bit of data from all of them. It's awesome, and it's all done really quickly, optimally, and it's super complex behind the scenes, but the math is done for you. Win. Remember before we talked about Cartesian communicators? Let's see an example of that in action. There's a command in MPI where you can have all of these nodes here send data to the one above it. So in this case, process 11 would send a little bit of data to process 1, or process 3 would send data to process 23 using wraparound. And so in this way, you can have all of them transfer a little bit of data with just one command. You don't have to type this separately for each process. You can just do one command, and all of them know how to do it because they have this topology, this geometry. You can also send it downward, which could be useful in other applications. Of course, you can also send it to the right. This could be useful for things. And you could send it to the left. So here, arrows to the left. Again, this is really useful for a lot of scientific applications because a lot of times, a little grid cell in a simulation will have a lot to do, has a lot of business with neighboring grid cells, but doesn't really have a lot of business with other grid cells somewhere else. Now let's shift our gears a little bit. We've talked about Pthreads, OpenMP, and MPI, and we've seen that they have a number of similarities and they're all really different too. But they all execute code concurrently in some sense. And they all have some problems that are common to them. One of those is a race condition. Now, a race condition is basically, we don't know the order that threads are going to be, or processes are going to be executed on CPU or on different CPUs. And so that means that different threads could be accessing a resource and try to change that resource, which could lead to unexpected results. Now let's do an example with threads. In the threaded example, suppose we have this right here, this little bit of code. We're counting up, and if we get to 10, we reset back to 0, otherwise we just keep counting. So it just keeps looping, counting to 10, reset to 0, counting to 10, reset to 0. We have two threads, thread 0 and thread 1, and we have the value just initially, x equals 9. So let's say the blue thread gets to go first. It executes the first line of the code, and that evaluates to false. And then the CPU says, okay, now it's thread 1's turn. Thread 0, you're finished for now, or you're not finished. Pause for now, wait, and we're going to have thread 1 go next. So thread 1 goes, and it evaluates x, is still 9. It evaluates that to false. And then the CPU says, nope, it's thread 0's turn. So thread 0 then goes, and it says, well, I know it was false, therefore I go to this section of code. So it evaluates that, and it then increments x from 9 to 10. But that might take a little while because the next bit is branching. It gets out of that if branch. It has to resume the regular code. So it waits, and the CPU says, okay, let's context switch. Now it's thread 1's turn. Thread 1, remember, is it evaluated that first expression to false, so it needed to branch and go to this part of the if statement. And so it increments x from 10 to 11. But now look. We've totally skipped this. We've counted from, say 0 to 10, and we totally skipped 10. What just happened? How does that work? And so there are ways to get around this, but we need to do that carefully. But this is an example of a race condition. You've just done something that if you were executing this in serial, it wouldn't make any sense at all, but now because you're doing this in a multi-threaded environment or multi-process environment, things got a little weird. And this totally happens. To avoid those kinds of problems and others, we have to make our code thread safe. Now the goal of thread safety is to, one, avoid race conditions, but it's also to avoid something called deadlock. Now deadlock is when two or more threads are waiting for something from one of the other threads, and they can't go forward, and so they're just kind of waiting for each other to do something. It's kind of like if you have a traffic jam. Another example that's not exactly deadlock, but basically gives you the same idea, is if you have a server and a client that are both waiting for the other one to send data. So the server is waiting for the client to send data, and the server and the client is waiting to receive data from the server. And the server is not going to send data until it receives data. And the client's not going to send data until it receives data. So they're both waiting for each other. And then they're in deadlock. So another goal of thread safety, so that's bad. Another goal of thread safety is to keep the threads running as much as possible. Don't make them all be waiting for each other. Waiting sometimes is good, but keep that short. Keep them doing useful things. Also, we want to ultimately avoid unexpected behavior. Now there's a bunch of tools, and it's beyond the scope of this course to elaborate each one of them, but here are some. Mutually exclusive locks. That means that if you lock a variable, you can say, okay, only one thread will access this variable at a time. You can also have, until you unlock it, until that thread says, okay, I'm done with this variable, now you can use it. You can also have something called atomic operations. So for instance, if you are calling a function or something, or incrementing a variable, you can say that this incrementing of x, x plus plus, that's going to be an atomic operation that cannot be interrupted by the CPU. The CPU will guarantee that this thread will complete that atomic operation, and so no other thread will be able to interrupt it. Kind of like a mutually exclusive lock, but a bit different. You can also have something called thread local variables. Now, normally with a multi-threaded application like Pthreads, all of the threads share the same variables. In OpenMP, we saw that you could have variables that are shared between the threads, which is normal, but you could also have private variables that are unique to each thread. So for those examples, you could have thread local variables where each thread has its own copy. So these are 3 tools that you can use to help with thread safety, but it's a complicated thing. It's wonderful, it's cool, but it's complicated. This brings us to an interesting question. If I want to write or read files from a disk, how do I do that? Normally, reading files from disk when you're doing multi-threaded or multi-process applications is pretty dangerous. Because what if one thread overwrites what another thread just wrote? Or what if the data is all out of order? For instance, if we're writing to a file descriptor like standard out, we saw that for all 3 of those libraries, the output was all out of order. Now that's fine if you're just reading from the terminal. The user can be smart and figure that out. But what if you're writing to a file, and what if you're actually writing data? That could be really bad and really weird and really confusing. Well, a simple solution that many people use is the following. You choose one thread or process to do all of the I/O, and all the other processes will send their data to that thread or process, and they'll just wait. So that one process will do its thing, open the file, write all the data, and then close the file, and then they'll all resume doing their usual work. This isn't really that great because a lot of threads are just kind of waiting around. And so you're just idling. And it's also a potential bottleneck when you're doing multi-process applications because it requires all of the processes to send memory to the master process. So that can be, it can take a lot of time to do I/O that way. MPI is awesome because it can perform collective or parallel I/O. The way that it does this is if you've got a huge bunch of data that you've got to split into, that you've got to write to file or read from a file, what it does is it actually assigns it splits up that file, and then each process works on a little bit of that file, reading a little bit of that data or outputting a little bit of that data. It's really, really cool and elegant. It requires that all the different processes or all the different computers have access to the same file system. For instance, in our CS-252 physical laboratory, when we were meeting together in the good old days, you could access the same file system from any computer that you logged in. So that would have been a great example to kind of demonstrate this. If you want more info, there's a link there. But I also wanted to give a quick example of that I experienced. So when I was working with my advisor at grad school doing solar research, we often had to use parallel I/O. So what we would do on these NASA supercomputers is we would have 200 processes running at a given time, and each one had to output, every so many iterations of the solar simulation, it'd have to output about 5 megabytes of data each. So 5 megabytes of data times 200 processes. We could, if we did that simple solution, that means that one master process, rank 0, would be getting 995 megabytes or something like that, about 1,000 megabytes of data from all the other processes, and they'd all, 199 different processes would be trying to send their 5 megabytes of data to this one process. It'd be this bottleneck. It'd be really bad. So instead, what happened is we would use the collective I/O commands in MPI, and it would allocate one file that would have about a gigabyte worth of space, and then each of those 200 processes would write their 5 megabytes to a certain little section of that file, so they wouldn't be interfering with each other. And then when they were all done, they made sure that they were all done, and then one of them closed the file, which is really cool and elegant. Now, speaking of supercomputers, most of the time when you do multi-threaded applications that are high performance oriented, you have to use a supercomputer. You can do some light multi-threading on your own computer for fun, multiprocessing, but ultimately if you really want high performance, you have to use a supercomputer. Supercomputers have different network topologies. Commonly they have something called a star topology, where there's one computer in the middle, and then that has branches and then goes to another. Each of those branches goes to another master node of some kind that has branches to other ones. So it's kind of like a tree structure, except instead of just having, say, 2 branches, it could have like 5 branches, and the next one has 5 branches, and so on and so on. And that could be good for certain algorithms. Grid topologies would be good for physical simulations a lot too. But your program, whatever it is, should be custom tailored for that supercomputer. If you have a program that's going to really use a grid topology, like say a solar simulation, you don't want to ask for time on a supercomputer that has a star topology, because then there's a whole lot of data that's being transferred from all the different nodes in that star topology through that one central star point node, the head node, if you will. And so that can be kind of a little bit of a bottleneck. So choose whatever works. On a supercomputer, you have dozens of users logged in at once, usually logged in on an interactive node or a head node, where you can just kind of play around. You can, you can edit text and stuff. You can use Vim or Emacs, but you don't usually run stuff on the head node because that will make things slow for everybody else. So instead, what you do is you submit a job request actually, and you ask to run your simulation or whatever on work nodes. A typical workflow is you SSH to the supercomputer that you have the account on, say for instance the Blue Gold supercomputer. You load modules and stuff, like say I want to use C++, I want to use Fortran, I want to use MPI. So you load these different modules that you might need. Then you develop and compile and test your code in the tiny work environment. Like on the head node, maybe you'll use a small cluster of maybe you'll request 10 nodes or so. Now when you're ready and you feel like your code is ready to really run, then you submit a job request to the system. And you can do this using a bunch of different technologies, for instance, Slurm or PBS. There's other systems as well. And basically you have to say, here's the resources that I want to use. I want to use this many processors or nodes. I want to use these kinds of computers. If you have a really big supercomputer, maybe some of them are, some computers have higher RAM. Other groups of nodes have faster clock speeds. Some of them are restricted or reserved for like government use or high security classified things, depending on the supercomputer. Usually you have to say what's the maximum time that this job will run. And so if you, for instance, your code gets into an infinite loop, the job requesting system will terminate it. Do you want to send an email? Do you have an email address? That way, if there's a failure with your code or if it completes, it'll send you an email. What's your preferred shell? Does it matter? Do you want to keep a log file for standard A or standard output? All these kinds of things. Do you want to submit it to a special queue or batch for different purposes? And ultimately, when you've submitted the job, you hope it worked because you only usually have so much time. And so you might be allocated, say 5 million CPU hours. And so every time that you request time, that time will get deducted from your quota, depending on the supercomputer. At any rate, if it worked or if it didn't, you get an email when the job starts or is finished or fails. So that's it for distributed computing, threading, MPI, OpenMP, Pthreads. For review, I'd like you to think about what situations you'd want to use Pthreads, OpenMP, or MPI for. What are some strengths or weaknesses of each? If you want to, think about some situations. What are some dangers of multi-threaded applications or programs? What is a blocking call? What is thread safety? Those are some things I want you to think about. Don't think about too many of the details yet. For practice problems, there's two levels of practice problems for today, and I don't encourage you to do this before the final exam, but if you're interested, here are some fun things you could try. One, choose to use either Pthreads, OpenMP, or MPI, your choice. Write a parallel program which creates a total of 10 threads, and then have each of the 10 threads print their number to the screen. Now this is basically what I've already done, so you could really adapt to these examples, the example code from earlier in this mini lecture, but you have to maybe install some software and stuff, but see if you can get that going. That's the novice way. You can play around with it, have fun. If you want to go a little deeper, I would challenge you to do the same thing, but now instead of having them output their hello world from thread number 0, hello world from thread number 9, hello world from thread number 6, instead of them outputting out of order, I challenge you to find a way to make them report or say hello in order, so ascending order, so thread 0, then thread 1, then thread 2, thread 8, thread 9. So to do this, you'll have to use blocking calls in some way. You have to basically have all of the threads or processes wait their turn to output to the screen. Now I'm going to show you an example of how to do this in MPI, but if you want to try using Pthreads or OpenMP, go for it. Now here's an example with MPI of counting in order. So this is exactly like the example from earlier in that you initialize MPI, then you get the number of processes in the MPI com world, and then you get the rank of each current process. So each process is going to say, well, which rank am I? And then each process greets the user in order. Now what I want you to think about is imagine that you have 10 different people in a room, each with a number 0 through 9, and a little piece of paper on their chest or something, like a little name tag, 0 through 9. In order for them to, and they're not necessarily all in a line, they're just mingling it out of order. And their goal is to be able to count from 0 to 9 and say, their number out loud. The way that they do this is each of them has to keep track of what number or whose turn it is to talk. And then they have to compare and say, okay, now it's process 3's turn. Am I process 3? Is it my turn? And then if so, they can talk. So what this does is, what's new about this code is you have this for loop that's counting. So I is the counting variable in the for loop, and that represents whose turn it is to talk. And so then each process checks and says, if it's my turn, if my rank equals I, if it's my turn, then it talks and says, hello from me. And then here's the important part. You have MPI barrier. Now MPI barrier is a basic generic purpose blocking call. It says all processes in this communicator, in this case MPI com world, so all processes have to wait until they get to this point. And if they don't get to this point, then it's deadlock. They just wait and wait and wait and wait and sit around. So wait till they get to this point and then proceed. And that's a way of synchronizing it and still making sure that they all go here and they're not just all counting and saying, okay, I counted to 9 first, yay, go me. But now they all have to wait, and so all of them have to wait until one of them has had a chance to speak. If it's not their chance to speak, they skip over that statement and they get to MPI barrier and they wait. And if it is their turn, they print out and then they get to MPI barrier where they rejoin the others and continue on in the loop. At the end of the loop, you call MPI finalize and you're done. So that's it. I hope you enjoy this, and it's been an awesome semester, and I really thank you guys for your time and attention. Take care. Jess out.